Also add Adaricheva. Now, how do you compare two values?
Kind introduction and everyone for coming for this Friday morning talk at Students Institute of Technology, hosting us this year. So what I will be presenting to you is some ongoing work that we started with my collaborator, Professor J.B. Nation, and we published the first paper on this topic in 2014, where this class of closure systems we call was unique criticals was introduced for the first time, right, in our paper. And since then, there was not so many results. It seems that it's a hard class and to work with, and I will be giving you some mild introduction into the topic. So we'll try to give our students present in the audience to follow. And the definitions are not too difficult, but that's during the talk is sometimes hard to grasp immediately. So always ask question if you need to clarify something. I will try to write on the board the most essential stuff, but I will be talking at the same time. And so maybe some of what is not written will be said. So the work that I will be presenting, like some new results on this class at the end of this presentation, is ongoing work with my collaborator from University of Marseille, Simon Vilmin. And it's a paper not ready yet, but we're working on it. We have some preliminary results, and hopefully this year we'll send it for publication. All right, so my plan would be to give you first introduction into the main definition, which is a closure system. And it has another cryptomorphic description through the closure operator. And then whenever we introduce the closure operator, we will talk about a classical object in this area, which is called a canonical basis. And that's all introduction, essentially. And then after that, I would be able to say what the UC class. That's a class of closure systems with unique criticals. So I will calling them UC systems. And so at the end, I will present some results on UC systems and plus problems, right? So it's fascinating that there is interesting problems that could be offered to combinatorialists. And it seems to be not easy, and we have different approaches. So we will see, like, if hopefully I will be able to present something like as a hypothesis and an ongoing, open question there. All right, so let me start with giving the definition of a closure system. So a closure system is really a set system. You have a set, everything in this talk will be finite, even though these concepts could be extended to infinite case. You have a finite set and you have a family of subsets. Well, it will be called a closure system. I'll say closure system as a CS, right? If it satisfies these two simple properties, first X itself, the set, belongs to F. And secondly, F is closed under intersection. So that means that if you have two sets in F, the intersection will be in F. Well, so the closure systems are really abound in mathematics, and so like giving you some motivation. So we have closure systems where they appear. Algebra, geometry, kind of pure mathematics. They appear also in some optimization, such as areas as databases very prominently, and in operation research. And part of that, what's going on in operation research, it's logic as well. And so as we go, we will need to see the other side of closure systems in order to understand how it appears actually in logic and operation research. Those optimizational problem. So I prepared there a few examples of closure systems. They are very small systems. A set X, either 4 elements or 5 elements. I think the most of what I have is 4 and then 3 element set. So what you see is not a graph, it's a Hasse diagram. So Hasse diagram is a way to present a partial ordered set. So partial ordered set is a set where you have an order. So you would say that something is smaller than another element, right? So here, because it's a set system, we have very natural order here. It's a containment order, right? So one set is contained in another set. So say if you look at this example 1, so X is a 4-element set, and the Hasse diagram tells you that the lower laying elements are smaller. So like the smallest one is empty set. The largest is X itself because it should be there, right, in the closure system. And then instead of using curvy brackets and commas, right, I will just write the elements that are in that set. So that's you would follow the diagram here. So this particular example of a closure system represents very, very familiar to everyone and like most prolific closure system with a property of being distributive. It's called distributive. Because it satisfies this law of distributivity. Okay, so before I will actually write what is the law of distributivity, let me say a few facts. The fact 1 is that closure system is always a lattice. So what is a lattice? Lattice is a partial ordered set where every 2 elements have a least upper bound and a greatest lower bound. And by the definition of a closure system, you do have intersection of sets that will represent the greatest lower bound for any 2 sets, clearly. But there is also a join operation, as we say, right? The least upper bound. Okay, so for this, let's just realize that if you have 2 sets, Y and Z, right, that get into F. So this is operation of a lattice, which is a least upper bound. Could look at your closure system for all sets that appear there that contain both Y and Z. So we'll take for all F such that Y and Z both are subsets of that F. Clearly, at least X is there because X should be there. But then it's closed under intersection, so you could take intersection of all such sets. And if you think for a second, this will be the least upper bound of these sets, right? So in F. So if I pick any 2 sets, I should be able to look at all sets that contain them in your family F. And that will be exactly the least upper bound. So this operation is defined, right, as a join as well. This is why this is not just partial ordered sets, they are lattices, right, in which you have 2 operations. So now using this, so operations of least upper bound and the greatest lower bound, right? So this is lattice operations. I could write what distributive law means. That means that if you have a join of A with a meet of B and C, then you could distribute this join over this meet. Also, what it actually means that because the meet operation is actual intersection here, And the join is a bit harder, but for the distributive systems, the join is exactly union. And so you could check, for example, that these two sets, they just union into 1, 3, 4, right? And there's 1, 2, like union into 1, 2, 3. And so throughout the system, you would see you just use regular union and intersection of sets, and you will get distributive systems. So you probably saw this law when you were dealing with sets, right? With the union and intersection. So this is like reflected in this law. So this is so typical because you would see this, this type of closure system where you work with sets with the joins and as unions. Okay, so let's take a look at example 2. So example 2, if you would have a vector space over a field with 2 elements, say it's a 2-dimensional. So this particular diagram would represent all possible subspaces of such a vector space, right? Because you would have vector 1, 0 with vector 0, 1, 1, 1, 0, 0. So this would be representing that a 0 vector, right, on the bottom, and this would represent a subspace generated by this vector and this vector and this vector. But then if you take 2 such vectors, the third is there. Therefore, the only other subspace will be the whole space itself, right? So this appears, as a classical result is also a matroid, right? So like flats of matroids, because this is the way to generate.
Sorry.
Yes.
Here. So first of all, per your definition here, so like the empty set is not required to be in.
It's not required, but you could always, for the given closure system, make it standard by removing some elements from X.
Okay.
And this is for that reason, like all my examples will have empty set there, but it's not necessarily, so it's not required.
So then how, like if you don't have a complement, if you don't allow for complements here, how are you defining the meet of 2 elements in the system?
It's just intersection.
Intersection.
It's
Okay.
just intersection, straightforward,
Yeah.
Okay. Okay, so this is example where the distributive law fails, but there is another interesting law in the using joins and means, which called the modular law. So this is some weakening of distributive law. I'm not writing it because we really don't need for today's talk, but if you hear about modular, it's actually some, again, the law which is weaker than distributive, but it's still quite strict law. So as you see that, it's where you could say, oh, maybe I see an algebra, right? So the example coming from algebra. Let's look at the next example. So this system is not satisfying, again, it fails distributive law here. And because it's, will not be just a union. But what we will see here that there is another weakening of distributive law, which is interesting for our talk today. It's called semi-distributive, join semi-distributive law. So I will write it, as like for the distributive, I will write that this law says if you have a join of 2 elements, A and B is the same as A and C, then this element also should be equal to A join and B meets C. So this is an example which in fact appears in geometry, and we also could say this is a convex geometry. So what is a convex geometry? This is a model, for example, of convex sets, of 4-element set. So if you look at the geometrical location of points, 1, 2, 3, 4, say on a line, and you just take convex subsets. This is a discrete set, right? So, but the convex means that there is a convex set on the plane such that intersects with those particular sets. So for example, you don't have 1, 3, because it should include 2. Or any convex set that has 1 and 3 would have the whole segment in between, so 2 must be appearing there. So this is a model of convex sets on this 4-element set in geometry, right? So the geometrical appearance. And so this is what the special, so there is an additional special property that should be in addition to this hold in convex geometries. But I'm not giving it because again, it's not so essential today. So this particular system appears in operation research because it's a manifest and a cyclic system. So I will give clarification what means cyclic. There is no cycles appearing, but we will need to further definition to come back to this example. And this example will be important for the talk today because this is an example where all the other properties failed. And in particular, as the join fails. That's important for us. All right, so how to show that it fails? All right, so we will take this as A. So we'll see how it fails, right? We'll take this set as B. I will take this set as C. All right, so if I take A and B and I take a join, right? So which is the least set in the system that contains both. I will see that it's X. There is no other sets contains both. And the same will be true for A and C. But if I take a meet of C and B, it will be empty set, right? So they don't have common elements. And the join of that set, empty set with A, is A itself. So you would have A on the right side, they would have X on the left side. So it does fail. So we will come to this example after we introduce UC systems. So now I will go into moving to closure operator. And so for closure operator, it's important. Okay, so closure operator. To say that it actually always appears when we have a closure system. So let's see how it appears. So what is a closure operator? It's just some mapping that takes a subset of your X and maps it into another subset, which is in your closure system. Okay, so let's imagine that we have this Hasse diagram, right? Say from empty set to X, this is your family. Like all those examples, right? But now sitting like on a scheme like this. So let's take any set Y. So you have X again, right? So your Y is a subset of X, but not in F. So it's sitting outside, right? It's a subset of X, not in F. Well, so we could look at all sets in F which include Y. So X includes Y and some other one. And because it's closed under intersection, there will be minimal one, right? So you would take all sets that are greater than Y and you would intersect them. So let's call it phi of Y. So that's our map, right? So which will map every subset of X into something in the family F. So phi of Y by the definition is just intersection of all F and F that contain Y. Well, so we showed that that's definitely will be element in F, right? By the definition, because it's closed under intersection and it's a minimal one that contains Y. What if the Y actually in F? If we use the same definition, that will be Y itself. So in fact, you could see that it happens, right? That that's specific property of those subsets that get into F at their fixed points of this map. So the map is defined by the same formula, but now we could recognize when the set is in F, when it's a fixed point. At the same time, the whole F is a range, the range of this operator, because everyone will map to someone in F. Okay, so that's a closure operator. So that's its definition. As you see, it's like really closely related to your closure system. So you could build it out of the closure system. The properties that every closure operator satisfies are three important properties: that it's always increasing. It contains y, but it might have something else, right? As you see, might have something else. It's monotone. It's an easy exercises for students, so you could try to prove it later. And of course, if you mapped anything to, you got element there now in F, you apply phi again, then you will get the same set. Right? So if you apply phi twice for anything, for any subset, you will get phi y. We call it idempotency property. Okay, so what we have, if we start with a closure system, then we could get a closure operator. If we have a closure operator, we could just take its fixed points and will be a closure system. It's also easy exercise. So there is this two ways of going from one to another. And let's say that phi of y will be called a closure of y. And so the sets in F will be called closed sets. Well, so let's discuss like what is actually an implication. So connected concept is an implication. It's just a formal writing z for two subsets of X, which is equivalent to say that the z is a subset of phi of y. Okay, so if y is not in F in the family, the phi of y, the closure of it, will need new elements to be added. So really that's what would these implications say. If you have y and it's not in F, it's not closed, these are new elements you have to add. By the way, you not necessarily need to say, oh, these are all elements that you need to add. You could just list some of them. So there is no restriction as like what you actually put on the right side.
So you're defining y arrow z means it defines if z is in the
Yeah, so this is actual
definition.
definition of
definition
implication.
of that, okay.
Yeah, it just simply means that you would have z elements, right? Everything in z is in the closure of y. So it's among those elements that you need to add to get the closure.
So
Yes.
it'll be like any sets between y and phi of y.
Correct, yeah. So the maximum you could put phi of y minus y, right? That's a maximum typically you would put there, but it's not required in implication. Well, so it kind of seems to be a partial information about your closure operator. It just addresses the sets which are outside of your F and tells the kind of giving you some information what needs to be added to get the closure. Well, so the fact that I had fact one, so let me just write fact two. Fact two, if I take any set of implications on the set X, right? So I could say, right, y1 implies z1 and z2, whatever. So I will write any set of implications on set X, and this will define some closure operator. That's unique. Closure operator could be defined by any set of implications. So to say that it's unique, it's actually, we could put some index, sigma, right? So the set of implications. So let's go to this example 6. So I'm giving you the set of implications on the 4-element set. And I'm demonstrating that this operator is uniquely defined. I pick any set in X. Say I have 1, 2. How I compute phi given this set of implications? Well, so I'm looking at these implications that tell me as soon as I have 1, 2, right, I should have something else. If I look at one of the implications that tells me something that as soon as I have 2, I should have 3. Because of this monotonicity property, right? It's not just for 2 itself, but for any set that includes 2, I would have to have 3. Therefore, I will just take set 1, 2 itself because you need to take it, right? It's in the 5. Union with this 3. And now let's see, we expanded it to the biggest set. And see, now we have 1, 2, 3. There are implications telling that as soon as you have 1, 2, 3, you should have 4 in it. So you're adding 4. Well, so now we have 4 and then we have 2. That the last implication tells that 2, 4 should have 3. Well, we already have 3, right? So we kind of don't need it. What about 1, 2, 4? So 1, 2, 4 is present now, like we could add 5, right? So we go and like checking all implications, see what we need to add more to, and then at some point we're finished, right? So we checked everything. Now we cannot apply maybe some of the implications. And so we just stop there. As you see, it's a unique set. This is well known in computer science as a link closure algorithm. If you're given a set of implications defining some closure operator, you go and compute closures. It's called link closure. It's a very fast algorithm. It's a linear time algorithm. So there's some closure operator defined. Yes.
Just so I don't know, it might be silly, but like for the sigma, the implications, can it literally be any, you could write down anything, arrow anything, just randomly generate, and there will be a way to do it. Right?
Always.
So there's not.
Yeah. So it's also exercise. I mean, usually we require that they are not empty.
Okay.
There is some generalization to say, oh, we could say we also could put empty on the left and on the right. It's a little bit, different concept, but more general concept. Yeah.
This isn't equivalent to the closure system you started with, right?
Here I'm not really starting with anything except implications.
But if I start with
If I start with these implications, right? I could define closure operator. As soon as I have closure operator, I have closure system. Because I just take fixed points of that operator.
I thought you were defining implications in terms of a closure.
Yes, I know. I will go back. But I just said like it's a fact too, to give you an idea, right? So you could start with anything and you would just generate. Yeah.
Okay.
But indeed, if you're given a closure system, you want to really define those implications, right? That follow that system. Okay, so let me just give you fact 3. Here, we said that it's a unique operator, right? They're defined by implications. If you have already closure operator, or any closure operator, phi on X, there's a numerous sets of implication to define it. I would say many, many sets of implications. Defining. This is what makes this area quite interesting from optimizational point of view. So how to, find this set of implications, right? That would kind of will be optimal, right? There's a different, ways of optimality, but one of the most important ways of optimality so it will be the minimal number of implications. Okay, so now we will be addressing it because this is famous theorem. Yes.
So I just want to ask a dumb question before you say, back at the example here, I just want to make sure I understand this right. So when you added 4 there, you use the rule 1, 2, 3 implies 4, right?
Correct.
Because we have 1, 2, and 3.
Correct.
If that rule didn't have, if we didn't have a 1 to start with, would that rule give us a 4?
Will not be applied.
Okay, so it has to be 1, 2, 3. Okay, thanks.
So that's good that you stopped me because maybe I will mention to actually illustrate fact 3 for you, right? Because We define some operator here through these implications. My claim is that I could modify it in your eyes right now. You will see that I could remove some stuff from it and it still will define the same operator. Because you ask very good questions, like, what happens, right? What happens, right? Well, so first of all, I will look at this last implication, what it says. If you have 2 and 4, you would need to have 3. But you already have a stronger one that says, already if you have 2, you should have 3. Therefore, this guy is really not necessary. If I remove it, I will get exactly the same operator. So now look also, because 2 implies 3, if I look at this one, this is a little bit harder to see immediately, but I'm claiming that I could remove 3 from here and make it shorter implication. Why? Imagine that I have 1 and 2 to start with, right? Let's see how I would compute when there's no 3 here. Well, so I would look at this one and say, oh, I would need to add 3 anyway through that implication. So now I have 3 is not really necessary. You could just use 1, 2 because it will be there anyway. So as you see, I found the way to remove 1 and make short intervals, right? And that's what people doing all the time to trying to optimize, right? Optimize implicational basis, defining the same operator. Moreover, sometimes people are actually working not with closure operators, but with formulas, because if you look at implication, it's a propositional formula. People just work with them and optimize formulas. So for example, in operation research, that's what the people work with. So they write formulas and they try to optimize their form, right? So they have less variables appearing.
Is that like SAT solvers?
Yeah, so it's possible. So because again, this is logic is highly using this type of, it's called Horn formulas in particular. So it's a Horn logic in particular. It's a very, deduction comes in a very fast algorithm, unlike other formulas. All right, so now I need to yes.
I guess if you start with 1 and minimize it, it might be the case you started to supply cells, you could have gotten a better result in the end. It's not like you're going to guarantee to get the minimum thing starting with something that works. Is that correct? I assume that's.
We could, I will formulate the theorem, famous theorem, saying if you start with anything, you could just get to that optimal guy.
Oh, you get to optimal.
It's not
anyway.
optimal, in fact, but it will be minimal, right? With a minimal number of implications.
Okay.
So I'm giving you that important definition before formulating it. So now we need to understand what is a critical set. So you have your closure system and a C, set C, which is not an F, is called a critical set. It has 2 properties. Okay, so let's just take a look again. This is our system. And this is your C. And this is a phi of C, identified, right, by that corresponding closure operator there. So it's called a critical set if you just take this F together with this new set C is a new closure system. So what it means, it will be closed under intersection. In other words, if I throw in this new set, all the intersections with other sets in F are already there. So either this is a set larger than C, then intersection is a C itself, or intersection is a closed set. So it's already in F. So it's a kind of minimal set to add the closure system to keep it as a closure system. And the second property, this phi of C, right? You might have multiple sets like this whose closure is the same. So this guy must be minimal from all of these sets possible, right? So you would say if you have C prime strictly smaller than C, then phi of C prime strictly smaller than phi of C. So it will not be the same closure. This kind of minimal set with respect to this phi of C. Well, so this set, in this case, if this is a C critical, that has to be a relation, like C smaller, right? Definitely. This set is called essential.
So both of subsets mean in there and not equal to?
Yeah, so they're not equal.
Right, okay.
So strictly containment, right? So it will be smaller closure. All right, so you could just go and identify all critical sets for your system. So now the theorem, here comes a famous theorem. It had two independent proofs. So this is a specialist in relational databases, and his book became very famous, 83. And he formulated the theorem in the language of relational databases, while Aix-Marseille, the two French computer scientists from Paris in 86, famous paper, it was in French. And it was published in some humanities related journal. And so therefore, until 90s, nobody realized it's the same result. Meyer is from Washington State. So they are really far geographically, different languages, different areas of research, right? And then nobody realized until 90s. Okay, so they say, if you take a set of implications such that you found all critical sets for a closure system. Here you write that this is a conclusion maximal possible, right? So this EI is just phi of CI minus CI, right? For all of them. So you just write these implications, all of them, right? For those critical sets. It's called canonical basis now these days. Is first has a minimal number of implications possible. Not only that, if you have any other basis, for your closure operator, right? So we're talking about closure system or operator here given, right? There is one-to-one relationship. I'm not telling you all details because it's a little bit involved, but if you have your sigma canonical and you have another basis, then there will be some subset here which goes into one-to-one correspondence. So you kind of need to, that's kind of confirms why that's a minimal. So, but there's a really close relationship between those implications that you would find in any other basis. So there is a one-to-one correspondence to some subset there specifically described. So this is famous result. It's kind of in the heart of theory of closure spaces, right? Closure systems. All right, so now having defined the closure, the canonical basis, right? So we've done the introduction. Now I need to hurry a little bit.
Sorry, quick question. These CI, what is it that we're assuming is a critical set?
So these are all critical sets for your system.
Okay.
Yeah, so I have to put maybe CIs are critical, all criticals, right? Critical sets.
Thanks.
You need to find all of them and you have to include them. So you cannot avoid any of them. Well, so we will see that there is a famous result of some in algebra, say, where people actually, if we translate it on this language. Yes.
Just very quickly. So this theorem is assuming you have started with a CS, right?
Yeah, so
But-
we have a CS, right? Maybe it was a closure operator.
Right. So then kind of, am I understanding the punchline where it's the systems of implications give you in the other direction, if you just gave me a system of implications, maybe with some restrictions, that will give me a CS going the other way.
Correct, yeah, because you will just take all closed sets, right?
Okay, so
You will
if I,
just take closures, so you will get all of them, yeah.
right, so then if I start with a collection of implications and then define my critical sets to be the left-hand sides of those implications, then that
Correct,
would, okay, yeah.
correct. So the closure system could be given in any of these two forms, right? But you could always get to the other form, right? You could get all closed sets, and then you should be able to figure out all the critical sets. All right, so let me just mention a couple of results where people really have some properties on closure systems like that, right? So they classify systems by using some properties like what I presented to you. Famous theorem of Garrett-Birkhoff of 37. If you saw this, I mean, I will formulate it very differently because I will just bring this more modern concept of canonical basis. He would characterize a finite closure system is distributive if and only if the canonical basis has the form AI implies BI. So it's a singleton here. That's important. That's a singleton. It's a if and only in state.
And this is also a single implication.
You could split, in fact, you could write AI implies, and if there's a 10 here, so you could just write 10 implications like that, or you could just combine them into one, right? So this could be, any set, while the left side is a single. That's how you distinguish distributive systems. Another theorem, that's a Marcel Wild, 2000. He developed the algorithm. Given canonical basis, one can recognize a modular system. I'll say fast, right? Fast algorithm. Because usually it's not the case for most classes. So there's effective algorithm to recognize modular systems. Now come as the join, right? So my work was JB Nation. We were trying to do the same with this law, right? Join semi-distributive law. Can we recognize if the canonical basis is given, can we recognize it as the join system? So far, we don't know if there is any effective algorithm for that. But what we notice in that paper, if your closure system is as the join, then the number of essential sets and critical sets is the same. There is only one critical set per essential set. Okay, let me demonstrate here. This is not SD join. So one of the critical sets here, set 1, 2 is critical. And if you take a closure, that will be X itself. 2, 3 is critical for the same X. And 1, 3 is another one. You have 3 criticals with the same essential. Therefore, canonical basis here, for example, will be 1, 2 implies 3, 2, 3 implies 1, and 1, 3 implies 2. Do you have 3 implications because you have 3 critical sets, but you have only 1 essential? Yes.
What's essential?
Essential is just a closure of critical.
Closure of the, oh, you're right, it's written right there. I missed it. Thank you.
Also, let's take a look at this as the join. All right, so I'm claiming that 1, 3, it's just 1, 3 is a critical, and it corresponds to this closure. And so there's a couple more. You have 2, 4. And this is a closure. Then you have 1, 4. And the critical is here. So I could write the canonical basis here. So this is 1, 3 implies 2. I have 2, 4 implies 3. And I have 1, 4 implies 2, 3. As you see, I have 3 critical, 3 essentials. So I have a unique critical per section. That is what we call UC system. Unique critical per essential, right? Okay, how much time I have? Okay, we'll try. So we introduce UC system. So the question, are these, like we definitely, according to the theorem, as the join, right? This is class of joint semi-distributive systems that we're interested in, is included in UC, but are they equal? It's very easy to see they are not. That's why critical example here, example 5. In example 5, it's a very small closure system. So you would have, it's actually UC, so I want to demonstrate to you, right? So what you have 2 implies 1, that's a first because 2 is critical. Then you have 1, 3 implies 2, because 1, 3 is critical. Then you have 1, 2, 4 implies 3. 1, 2, 4 is critical. And finally, 4 implies 1. So you have 4 critical sets here. And so if we look at the closures, like you just need to compute the closure of left side and check, oh, they're distinct, right? All of them will be distinct. So you would have this one, this one, this one, and this one. And so all essential sets. The closure of these 4 critical sets. So this example shows like it fails as disjoint, right? So this is example 5 is here. All right, so finally I have possibility to present you new results, right? That we were able to achieve with Simon Vilmin. Okay, new results. All right, so the first theorem. All right, initially when we worked with JB Nation, we thought, oh, maybe this UC class, it's a bit larger than a joint semi-distributive class. Maybe we could find some weakenings of this law to define it, right, through some laws. Turns out this is not the case. So the theorem claims that if you take any finite closure system, any, I should be able to, so this is say on X, right? I should be able to find UC system on a bigger set X prime, such that this system will be reproduced here as an interval. So it will be isomorphism between this interval and closure system here. Therefore, there's no hope that we could try to define it by some properties, which usually, if you true on something, that is also on a subsystem is true, right? It's true because these laws that I gave to you, these are universal laws. That means that they preserved on subsystems, right? In intervals in particular. So the proof is actually very beautiful, but I don't have time. I thought like maybe I'll include at least one proof, right?
Did you put it up on archive? So
It's not an archive yet. I thought, oh, I will show it on this talk because it requires 5 minutes, but I don't have yet. If I have later, I could show. Okay, if you're interested. Okay, so theorem 2. You would see then, you would think after this theorem, oh, it could be anything, right? Surprisingly, the class kind of follows the lines of as the join class, nevertheless. Because we were able to show that if you take another class, semi-modular, I mean, I'm not telling it, but it's a bit weaker than modular. Semi-modular, this is a law that holds on all flats of matroids, by the way, right? So if you intersect this class with SD join, you will get only distributive lattices. That tells you how different generalization of distributive law is this and that. But it turns out I could replace SD join class by UC, which much larger class, I will get the same. So if I expand my SD join class to UC class, intersection with a semi-modular class, still the same. Okay, semi-modular simply means that if you have any points like AB, intersection, and join, if between these two vertices there's nothing in between, we call it cover, right? Then there's also cover on the top of that square. That's what semi-modular means. Okay, so the other result, if you instead of semi-modular take lower semi-modular, which is just reversing the arrow down. When you take these two classes, you will get convex geometries, famous class, right? That will a lot of interest in this class. Turns out, again, you could just replace it with UC, and we'll get the same. So kind of if you put on top a second property, nothing changes. These are kind of hard results to prove, so I'm not really attempting, right, to show you the. And say the third result, we have a couple more kind of in working, and it shows everything like behavior with respect to other classes, similar to classes disjoint somehow. So it's paradoxical together with theorem 1. So you may have meet semi-distributive law, where you change all the joins to meets and vice versa, right? So take the same law, but change all, it's a dual law, right? We call it dual law. And the same happens here. So this is also famous class called semi-distributive. And this is the same intersecting with UC. And then the last result is kind of also kind of negative to the one which in the theorem 1, kind of algorithmic result. So what in computer science quite often is popular is to look at these two representations, right, of your closure system through F, right, the closed sets, or through closure operator. Well, if you have closure system given by family, people say you don't really need the whole family, you just need the ones which are meta-reducibles, because It's closed under intersection. So what is a meter reducible? It's a set which is not a intersection of larger sets in this family. They're called meter reducibles. Then every element, like every set in your family now is the intersection of meter reducibles. Because you could use operation of intersection, right, to generate the whole family. So therefore, people usually look for a smaller family, which are meter reducibles of this path. While on the side of a closure operator, people look not closure operator defined for any set, but just some implicational basis, right, which is considered to be like a partial information. So algorithmically, people looking, what if we, here we have this and produce this by some interesting algorithm, which is fast, and vice versa. So can we go from one representation to another quickly? Most of the cases show it's like NP complete, right? So like very hard. So we have the same result, kind of negative result, saying, oh, if we have X given by your meter reducibles, then producing, if we would produce canonical basis, we would recognize that it's UC system very quickly, right? Because we just need to see that closures of left sides are the same. So we're asking the question, can we recognize UC systems through that, right? So through closure operator is very easy to recognize, but what can we recognize is through meter reducibles, right? If this is given to us, can we do that? This is negative results, QNP complete. So very easy when you have canonical basis or any other basis, because you could get canonical basis quickly from anything, from any other basis. And then you just check that the closure of left side is different. That will be UC system, right? But from meter reducibles of your F, that's very hard. So these are new results. I only have 2 minutes, but I could formulate if we want, I could formulate the problem later. So just maybe finish now, and if anyone interested, I could talk about open problem for combinatorialist later. Thank you. Yes.
I have 2 questions. So the first question is, what made you get interested in closure systems?
Yeah, it's a very good question. I mostly was working in universal algebra and lattice theory for most of my career. And then I happened to go to some meeting, and I had a ride in a car with a person said, I have a room in my car. Let's go back. Like, I'll drive you to Chicago, right? From Urbana-Champaign. And while talking in the car, he mentioned some papers to me. He said, we have a question to you because you understand lattices. We don't understand lattices, right? And I said, yeah, sure, send the paper to me. That was the way. Like, I got the paper, became very famous. And it was published in 2010. And again, these are 2 French authors. And I read this paper, and from the moment I finished reading this paper, I said, I know some answer to this, to the question that they're raising. And that was got me into that. But it took us a long time to actually understand the canonical basis, because we never heard of that before. And so we started working on that, and it seems to be like very stimulating research there. Kind of goes now parallel to some the other research that I do.
And the second part, is that just a translation of Birkhoff's like famous theorem? Where
Yeah.
like it's,
Yeah.
Okay.
Exactly, yeah. So he proved that like his original result is, say, it could be generalized to some infinite cases, but in finite case, a lattice is distributive, if and only if it's represented as a ring of sets. So ring of sets is there, like every element of your lattice could be represented by a subset that where operations of join and and meet, right, of lattice operations, actually union and intersection. He actually gave a precise representation how to find this, the base set and what are the actual sets will be there as a closure system. So this is their famous result. Yes.
Is any of this stuff similar to like stuff like filters, where filter thing is close to an intersection and has empty set, or ideals are the opposite? Seems similar, but a little different.
Yeah, they, very different from
Very
filters.
different.
Very different from
Looks a little
filters.
similar, but they're very different.
Very
actually.
different, yeah. Yes.
In theorem 2, are both equalities part of the theorem, or was one known and you proved the UC version? Or
So these are known.
that one was known, but you said
Yeah, these
UC,
are known,
if you
very
do
well
UC,
known.
Okay, that's
This is a
known.
hierarchy of classes, people well aware of this,
Yeah.
right? And that's much bigger hierarchy. I'm just showing you the portion of it, right?
So you-
But surprisingly, we go in every single portion of it that we knew, which relates to this SD join. And after some work, you show that you could replace it. So you don't have extra sets, extra closure systems there.
The UC refers to the closure system. I forgot with the criticals.
It's a unique criticals. It's called unique criticals, which means that for every essential set, there is only one critical set. As I mentioned to you, modular is not like this, because for this essential set, you have 3 critical sets. Yes.
So just make sure I understand, the idea here is that like these are whatever the extra thing about UCs, the extra ones that you
Yeah.
get
Yeah.
are not gonna be semi-modular LSM,
Exactly.
SD. So these example 5 type things are
Mhm.
not any of those.
Yeah.
Do you have any other characterization of example 5 type issues, you
So
know?
this is what I
I
wanted
guess
to
that's
do
the
at the end,
question, right?
for which I didn't have
Like,
time.
what's the deal with them? Yeah.
But I could say very quickly, right? Because you
Yeah.
asked. Okay, so if I may, because the next speaker, right, I should start,
Go
right?
for it.
So for example, we interested in closure systems which are atomistic. That means that singletons included in your F, and which will be minimal UC systems on that given number of elements in your set X, right? So you have n elements, you include all singletons in your closure system. That's kind of restriction, right? And you want to count how many minimal UC systems you might get. Minimal means that if you remove any element from there, it's not UC anymore. And we did it for n equal 4, and we found there's only 3. This minimal UC systems. One of them you see here. It's a minimal UC system on the 4 element set. It's atomistic. It includes the singletons, as you see. And so you would get that one, and we found 2 others. This one as disjoint, right? It's semi-distributive. 2 others, one of them as disjoint, the other not. Now question, what if I go from N4 to higher to any N? Can I enumerate all of them? Seems to be a hard problem. We have a few approaches. We have hypotheses about that, but we don't know how many. It might be a new sequence, right? And the sequence, possibly, I don't know, or maybe we'll find something in the existing sequence and it will give us some input then. But seems to be, it relates to this other problem, right? So if you have an operator which you recognize, it's a UC system, can we reconstruct this meter reducibles fast? This problem, like if we solve it, kind of gives us some possibility that for this class, we might have reconstruction of meter reducible closed sets given implicational basis. And so this is why, I mean, it's independent, the kind of problem, combinatorial type problem, right? To find all of these systems, which are minimal, but it might help in understanding what do we have any hope here, like in an inverse direction. Questions?
Okay. Yeah.
Okay, Yeah, so let's just,
I'm just gonna run with that.
yeah, please do.